Hi, my name is Nathan Eick from Aerial Services, and I want to talk about where do UAS stack up versus manned aircraft in remote sensing. I want to talk in general about three geospatial products. In my opinion, the most common is Ortho Imagery, basically a flat 2D composite or mosaic of images taken from above, and those are usually assembled into one giant ortho mosaic. I also want to talk about elevation or 3D modeling, typically of the ground for engineering purposes, but also maybe of structures or power lines. And finally, I want to wrap it up talking about mapping, which is vectorizing geospatial data in 2 or 3D. That mapping is sometimes a combination of ortho imagery and elevation and 3D modeling. So the first part, ortho imagery. That's the process of taking airborne pixels and projecting them in the right place on the ground. You need three things for that to happen. So you need the airborne location and orientation, or the EO, external orientation, to determine the location of the sensor. You also need calibration information for the lens and sensor so that the pixels within an image, that's a 2D unprocessed image, can be projected to a spot on the ground with a given angle. And you need the surface to determine the location on the ground to figure out exactly where that angular pixel projects itself to on the ground. So that way your geospatial products, or that way your ortho imagery, is geospatially correct. Spatial resolution is generally given in terms of GSD. For satellites, that's on the order of 1 meter, or 1 meter per pixel. For manned fixed-wing aircraft, that's generally in the range of 5 centimeters and above, and you can't usually go much lower than that due to the speed of the aircraft. For manned helicopters, because the helicopters can fly a lot slower than fixed wings, you can get GSDs in the 5 millimeter and above range. UAS, which are some of the slowest flying aircraft, can fly lower and slower and collect down to the 1 millimeter GSD range. Capacities of these systems for ortho imagery are generally sun angle based. You have to be collecting during daylight hours in order to take ortho imagery. The technology to do that at night doesn't exist currently. In the manned systems, the capacity is based on the flight time in the aircraft, and typically the flight planning parameters include a 20 to 30% side overlap due to very accurate EO and IO. Those are your external orientations and your internal orientations or calibrated sensors. And you have existing or a lidar surface included with that, so you can fly at much lower side overlaps. We typically fly manned aircraft frame-based systems at 60% front overlap for redundancy and the ability to autocorrelate or generate a better surface than the existing DEM. We could fly as low as 20%, but because it's not any extra flight time, we typically fly at 60%. We also have beyond 350 megapixel sensors, so there's fewer frames and less computational power needed to process versus UAS. One 350 megapixel frame is easier to process than 10 overlapping 35 megapixel frames. We don't need any additional overlap to build a 3D surface to orthorectify the imagery like unmanned systems do. Altitude is unrestricted, so downsampling isn't needed. We don't have a 400-foot ceiling. We can typically fly as high as we need, just depending upon our aircraft. And that lets us be more efficient. In general, ortho imagery is not a true ortho, so rooftops or buildings may lean. In order to make a true ortho, it takes a lot more work, and it takes a much more involved DEM in order to make sure that the rooftops or the buildings do not lean. Manned aircraft sensor introduced fewer seam lines, both with frame-based and push-broom sensors. Manned aircraft are, however, GSD limited. And that's when we get into the argument of manned versus helicopters. Helicopters fly slower, and they can also fly lower legally. So that allows them to collect data at a much higher resolution, although it takes longer and is much more expensive. Let's talk about some of the details of the capacity of unmanned systems. Unmanned systems are typically flown at 60 to 75% side overlap to self-calibrate the sensor on every project. 75% front overlap is very common for 3D surface reconstruction. UAS are line of sight limited and forward speed limited for a variety of reasons. Those reasons include blur because the sensor does not have forward motion compensation, rolling shutter distortion that affects both the EO and the IO, Altitude and field of view also limit UAS, and sometimes speed does as well. 15 centimeters is generally the GSD for multispectral sensors, all the way down to 1 centimeters for fixed-wing aircraft. Below 1 centimeter GSD generally requires a multicopter or a hovering aircraft of some sort. Unmanned aircraft also requires AT or aero triangulation and significant processing time, often more than collection time. To increase the capacity of unmanned aircraft systems, a few different pieces of technology can help. IMU and GNSS tightly coupled solutions that are post-processed can help reduce the amount of side overlap necessary. Calibrated stable cameras with leaf and mechanical shutters also help increase the stability of models and accuracy. Cleaned DEMS without above-ground features reduce the number of artifacts in UAS imagery as well. That wraps up our topic about ortho imagery. Section 2, Elevation and 3D Modeling. There's two primary ways to determine 3D information from remote sensing. Number one is photogrammetry. It's traditional, but it's recently been significantly automated. And there's lidar. It's newer and advantageous over lightly vegetated areas. Spatial resolution of lidar products is generally in terms of PPSM, or points per square meter. That's how many points of a point cloud are within a specified area, a square meter. Projects requiring less than 50 PPSM can generally be flown with fixed-wing manned aircraft. Projects requiring greater than 50 PPSM generally must be flown with helicopters or UAS, due to the fixed-wing manned aircraft only being able to fly so low and so slow. Photogrammetry can produce point clouds up into the hundreds of thousands of PPSM, but the error from those is generally much higher, and there's very little vegetation penetration. It's not generally comparable to lidar, so we're going to talk more about lidar in this section. LiDAR capacity for a given sensor is generally based on two things: PRR, or pulse repetition rate, and the range of that sensor. With manned aircraft, they typically fly at 20 to 30% side overlap, and that matches with ortho imagery. The PRR, or pulse repetition rate, is 300 kilohertz all the way up and beyond 2 megahertz, often with dual channel systems. Those provide very even point cloud distributions. The range is also in the thousands of meters. Because it's more difficult to identify tie points in LiDAR point clouds, highly accurate IMUs are used to aid in processing. With unmanned systems, LiDAR is generally similar, but it's typically flown at 30% or more overlap due to wind angle corrections and non-gyro-stabilized sensors. They also have a 360-degree field of view at 400 kilohertz for the pulse repetition rate. But only 100 kilohertz of that is usable because only 90 degrees is generally in the downward field of view. They have a fixed direction with a less even point cloud distribution, and they don't have as much stabilization, so the point clouds are not as uniformly distributed. Heavy lift UAS and sometimes custom UAS must be used as LiDAR sensors are much heavier. They are also much more expensive. The workflows for processing LiDAR data from unmanned aircraft systems and manned aircraft systems are generally the same. Section 3, Mapping. Mapping is the creation of simplified vector products that are used in many industries. Mapping is often done directly from ground surveys. However, airborne products are also able to produce similar or better results, but on a larger scale. Mapping includes classifying point clouds as well as generating contours and drawing points, lines, and polygons. Maps of 2D ground features can be created from accurate ortho imagery. 3D features, however, are more often created from stereo photogrammetry by triangulating points using 2 or more overlapping photos. Mapping is easier from LiDAR with even point distributions, so manned LiDAR systems generally have an advantage over unmanned. Manned photogrammetric systems also generally have an accuracy and capacity advantage over unmanned systems due to their calibrated construction and high resolution. Just like in ortho imagery, it takes less effort with few high-resolution frames as opposed to many low-resolution frames collected with UAS. Mapping selection accuracy is also influenced by GSD, and from our comparisons above, UAS may still hold an advantage in certain scenarios. To wrap this all up, UAS and manned aircraft are both legitimate platforms to conduct remote sensing. In ortho imagery, fixed-wing manned aircraft with state-of-the-art high-resolution sensors dominate the market at GSDs above roughly 5 centimeters. The processing time and accuracy over very large areas are unparalleled, but the equipment is expensive. UAS can be accurate on smaller jobs and sub 5 centimeter jobs, but it takes significantly more processing effort to ensure this quality. In 3D elevation modeling and lidar, manned aircraft also dominate the wide area market with their long range and high pulse repetition rate sensors. However, they can only be flown so low and so slow. Helicopter and UAS platforms do compete in this low altitude collection where high point density, more than 50 points per square meter, generally is needed. Mapping, a derivative product from photos or lidar, can be done with any system. The time and effort it takes to accurately map often depends upon the quality and the size of those inputs. Either system can be advantageous, and that depends upon the requirements of your project. I'm Nathan Eick, Geospatial Products Manager at Aerial Services.